All right, happy Thursday. So just a reminder, I am giving out extra credit for the speaker talk that we had. I think it was 2 Fridays ago, since last Friday was Thanksgiving. So don't forget that opportunity. So extra credit, and we'll say 5 points on final. And the speaker was Joanne Reed. And so you should be able to find it on the YouTube on my channel. And so it should be there. So if you missed it live, you can go ahead, check it out. And then, like I said, just give me 2 sentences so I kind of know that you checked it out a little. And like I said, that's worth 5 points. Yeah, emailed or physical copy, either way, just get that in. And I'll accept those, up until the end of the quarter, basically. And same thing for all your other work. So I have finished grading everything that was handed to me. So I'll try to furiously hand back papers, but I also did want to do a fun demo. But yeah, try to get your papers from me, especially I know some people really wanted their stuff back, and I do have it. So, and then, oh, I did post. So people were asking about reviews. I'm still kind of working on it. I posted this like quiz that I had that was there. It's like a practice quiz on Blackboard. If you wanted something papery, I can also post something paper, but it's just not in like the pretty format like the first one. I may try to fix the formatting, but yeah, otherwise I'll just kind of post what I have for people so you can review and get started. I know we're running out of time with the quarter. Other questions, comments? So yeah, just work to get everything in, just the final push, right? Turn every assignment in that you possibly can. Watch the percentages of your grades. So obviously the exams do carry the most weight. All right, so we left off with our bond energies. And again, if there are questions, let me know. And so basically what we can do is we can figure out our enthalpy change of our reactions. And so our hint here is, so to break a bond, that is always an endothermic process. So, right, positive input of energy. And then when you make a bond that is thermodynamically favorable, we'll kind of look at why that is more next quarter when we actually start making atomic orbitals into MO orbitals. So that is going to be exothermic. So you get energy out with that process. So formally with the negative sign there. All right, so let's kind of look at that. And so this is kind of a visual, and we can go through the math on this one. And so it's also helpful, especially when you're first kind of learning, or maybe even you found this if you had lab on Tuesday and kind of where did these equivalents come from. It's helpful to draw it out so you can actually see explicitly like what's being broken, what's being formed here. And so looking, we could maybe write this overall reaction that we have displayed here. And so we have methane, so CH4 plus chlorine gas, and we're just trying to make chloroform here. So it gives us CH3Cl, and again, that might be more helpful to write out in a rough Lewis dot structure format so we can see the bonds. I'm not caring so much about shape right now. I'm just looking at connectivity. And then plus HCl. All right, so now let's kind of analyze what had to happen. And let me redraw this again, just so it's clear. All right, so we have methane. And now just comparing these structures. So we had to break at least one of these CH bonds. So that's energy in. And then, right, we can quantify that. So we'll do that in a second here. We're just kind of walking through it. I'll rewrite our chlorine. Okay, so we can tell that's a single bond. And so we're also going to have to break this bond, right? And then in turn, we're going to get energy back in our formation of our carbon-chlorine bond, and then also formation of our HCl bond. And so they kind of have this done graphically, so now we're going to go through the numbers. But what's shown here, well, you tell me, so right, products are lower than the reactants, so what do we expect this reaction overall to be? So exothermic, right, so losing energy, so exothermic. If we were looking at a diagram, right, our change in enthalpy here, again, that's how much heat is lost. Let's double check that now. So let's go through this. And so I'd like to set up our two columns. So the bonds that are broken, and again, that's energy in, so positive sign. And so now let's refer to our chart. And on an exam, right, if you had this question, I'd probably supply what the bond energies were, so you're not like hunting through your book for anything like that. And so according to this chart that I have here, again, right, you might see different numbers depending on the chart. And obviously, again, watch your units. So a CH bond is worth 414 kilojoules per mole. So I'll just write that. And we just had one CH bond. And then we also had to break a chlorine bond here. So again, single bond, so I'll go back to my chart. So chlorine-chlorine bond is 243 there. And so we can go ahead and add up how much energy total we put in, right, for breaking our bonds. So 414 plus 243. So 657 kilojoules total. Again, going in, so I'll put a positive sign just so that's really explicit. Now let's compare that with our bonds formed. So again, getting energy back out. And so looking at the bonds we created, so a carbon-chlorine bond. So let's see how much that is worth. So carbon-chlorine down here, so 339. And then we also formed our HCl bond. So looking at that, where's HCl? So 431 kilojoules. And I'll add those numbers together, and then I'll put a big negative sign on that. So 339 plus 431, again, all that back out. So that's a total of negative 770 kilojoules. And so then that means our overall change in enthalpy, bonds broken plus bonds formed, so 657 plus my negative 770 kilojoules. And so now let me get our final answer. And so that gives us an overall change in enthalpy of negative 113 kilojoules. And then, of course, right, that would be per 1 molar amount there, right? So it's always based off of our formula there. So that's the other key. Questions on that process? Yeah.
Couple of few chapters back when we were doing calculating the ionic bond energies, we were working with like attojoules per bond. Are the kilojoules per mole values related to
They would be like related in some sense. Like if you were really bored, like maybe you and I as an aside would have to like do that calculations, because yeah, that would be like attajoule per one atom. So then I would probably start by multiplying it by Avogadro's number. But of course, I don't know that that's like just simplifying it as a two-body Coulombic attraction is kind of oversimplified, right? So you could like at least estimate it. But yeah, that's kind of a rough idea. Plus, these are also covalent bonds, right? So there are going to be some differences in that. But you're kind of on the right thinking of the scale, right? So you want to be thinking that yes, that's the correct scale that we're working on. And so if we're looking at a molar amount, yes, you would just multiply it by the molar amount, and that gives us kind of the equivalent scale there. So good thinking there. Other thoughts, questions? So see if we can try it for this reaction now. And so now we're generating hydrogen gas, so methane plus water gives us H2 and CO2. So maybe go ahead and write down this reaction and write down the balanced equation. Again, it might be helpful to physically write out things. And then once you get a second to copy this balanced equation, I'll kind of scroll back up so you can look at the chart. And your book should also have a similar chart, though. Oh, super reduce. So not. Yeah, I mean, you can start Googling the internet. These are standard values. Yeah, so on that note, sorry to break your concentration. So NIST is always a good website to look for standards such as this. And so just kind of an example, right? This is a whole huge publication of every single bond dissociation energy you'd ever want to know. Plus, it cites the publication, so then you can actually look back if you were really bored and wanted to check out those experiments. So just kind of for your information. All right, so let's kind of see how you're doing. And so I'll just start sketching out what I did. So I'll just, again, draw it out clearly for now. 2 equivalents of water. And then I am watching the chat. All right, so something like that. And so let's make a couple of notes. And so if you look at your little chart here, we have the value for CO. And so this CO double bond here tends to be in like carbonyl complexes like so. We'll kind of get there in organic chemistry. But it has a specific value for CO2, so we want to use that one in this case. So just kind of looking at things. And then other tricky parts were that we had to break, right, 4 OH bonds. And so that could have been a little tricky to see. And then, okay, so looking at our bonds, so we also need to break 4 CH bonds, correct, right? Because it's comparing our structures. We have no hydrogens attached anymore. And so I'll just start my bookkeeping. So bonds broken. Big fat positive sign there so we don't forget. So 4 CH bonds. And you can feel free to yell any bond energies at me. So 414. So 414 times 4. I'll do that at the end once I plug it in. And then again, right, 4 OH bonds. And so good, so let's look at that. So OH, where's my OH single bond? So 464 looks like. And again, times 4. So let's see how much energy in that was. So 414 times 4 plus 464 times 4. And so I get that large number. So 3,512 kilojoules. And again, that's in, so endothermic. Questions on that so far? Sorry, I don't want to speed through. And then bonds formed. So now let's see how much energy we get back. And so we have 4 HH bonds that we made. So let's see how much that is worth. So 436 times 4 again. And then 2 CO bonds. And again, it's our special CO2 number. Oh. Oh, it's kind of hidden. It makes a little, like, just a little star here. And I'm not sure if that's in your textbook. I would have to double check that. Again, on an exam, I'll provide whatever value you need for this. So yeah, $7.99, and that's for 1 CO in CO2. So yeah, this is kind of cool, but you can kind of measure the strength of the bond through IR stretching frequency. So this is a really cool characteristic group. Like I said, you'll talk about it a ton once you move on to OChem. And so 799 times 2. And so let's see what we get. So 436 times 4 plus 799 times 2. And so now we should get 3,342 kilojoules back out. So negative sign on that.
Sorry if you just covered this, but are we times it by 2 if it's the 799 for the whole CO?
No, it's for just one CO bond. Yeah,
Oh,
so yeah, so it's kind of confusing and it makes more sense. I was trying to say like compare it to this one, right? So this is in a compound. So this is 736 and I would expect it to be slightly weaker in a compound for reasons that I won't go into right now. And so then CO2 it's going to be slightly stronger at 799 and yeah, it's significant enough that they made a point of it, but like I said, you'll get to COs. Well, we'll talk about it ourselves probably third quarter, but you'll get way more into it with OChem and pi back bonding and all these terms that, like I said, we don't want to delve into today. All right, excellent. So now we're here. So now let's add these two to figure out our whole change in enthalpy of our reaction. And so now I'm just going to times it by a negative sign so I can have my signs. And now add it to the endothermic part. And so now I get an overall change of 170 kilojoules for this reaction. And again, based off of this stoichiometric amount, so 1 mole of methane and 2 of water. What else can we say about this? And obviously endothermic reaction, so right, does require heat. And again, you could put a little heat thing if that helps you. Questions about this one? So ask questions. All right, let's look at our last bit here. And so of course this is kind of what we did with our lab. And so we'll look at some math problems with it. And so again, we're measuring our enthalpy, and then we just have our caveat statement, so constant pressure. So again, just assuming not a large change in volume of gas. And so, right, you had something like this. Obviously, it wasn't a styrofoam cup. It was more the smaller styrofoam block, or you'll do it today if you didn't do it. And so part of the concept and how this all worked and what you're trying to do, right, was quantify how much heat, so your change in temperature that the water was gaining. So, right, obviously you're measuring the heat gained of the surroundings, or solution as we have it in this equation. And then obviously however much the reaction lost, all that goes into the solution. But that's also right why we had to do the little calibration for the calorimeter constant to figure out how much was lost to the calorimeter, since right this is not innocent in this process. And then we can, once we get Q, right, so Q again is just our heat or enthalpy, so this is something in joules. And then of course, right, we can quantify this and relate it back to specific heat of elements, right? So then this is giving us like how much an element will change in temperature. And specific heat is just a property, right? Specific heat. And so every element compound has a specific heat, so you would either look it up or, right, you can start to kind of compare relative specific heats. Let's see, I don't have, oh, here's water. So water is down here. So water has a high specific heat, 4.18 joules per gram degree Celsius. And again, this would be mass dependent. So that being said, it depends what units your specific heat are given in. Generally, we'll see it the joules per gram degree Celsius, but again, just be aware, right? You could pull up any reference sheet and it could have different units. You never know. Just keep an eye out for that. Then, so we could either calculate, right, either one, our change in temperature, our mass, kind of, obviously we have this equation, so we could solve variables as needed. Obviously metals, right, have a lower specific heat, so that's kind of why they heat up quickly, or if you touch cold metal, it feels cold to you since it's sucking in all your heat very quickly. Versus, right, water has a high specific heat, so that's why the coast is the best, right? Helps regulate our temperatures, so we don't have wild swings in temperatures, so acts as our heat sink. All right, so let's look at how we would go through quantifying some of these. And like I said, you basically did this in your experiment. And well, you did this actually experiment, right? So you did this, or you will do it. So reacting magnesium plus HCl, and again, right, that makes magnesium chloride plus a little bit of hydrogen gas. And so they're using a much larger amount than we did. So again, just kind of things to note for yourself. So this is a scale of 0.158 grams of magnesium metal, and then with enough HCl to make 100 mils of solution. And then, right, so this is basically your solution and how much water we have to heat up. And so, right, we tend to assume that our HCl solution is similar to water for our specific heat. And so, right, we can use that. Yeah, HCl is sufficiently concentrated, so the magnesium reacts. This caveat is in there because, right, we have to have it go to completion. Again, you'll find that this is somewhat of an issue in your lab, either Tuesday or today, where that's why I kept saying, use a small piece of magnesium, use a small piece, because you only had 2 mils of 1 molar solution, so you have to make sure that it completely reacts, right? So we're making sure we consume it completely. We know the moles that were consumed, so now we can quantify that heat properly. And so then in our problem here, the temperature of our solution rises from 25.6 degrees Celsius to 32.8. And then so it wants us to find our change in enthalpy of our reaction. So see if you can do that. You should have kind of all your pieces. We could go back up to this. I'll rewrite our Q equals MC T. Again, we're C is specific heat. And again, formula more dependent on these units than anything. So that's, again, where this formula is from. All right, try to work that out. actually. All right, let's see how we're doing on this one. And so again, right, we can plug it into our formula here. And so a couple of things. So obviously, right, we have our specific heat here. That's given to us. And then what is our change in temperature then? So 7.2, excellent, degrees Celsius. Oh, and just a note for these, right? So when we're looking at the change in temperature, so it is in degrees Celsius, but Kelvin and Celsius, right, do track the same, as in, right, 1 degree difference in Celsius is 1 degree difference in Kelvin, but obviously that would not be the same for Fahrenheit. So, right, it's okay to kind of mix and match Kelvin and Celsius here because we're just looking at a change in temperature, but otherwise, yeah, usually you want to stick to one or the other. Generally, you want to be in Kelvin for thermodynamic reasons, but all right. So, and then what is our, well, it does tell us here, because I was going to say, right, what's our mass amount, right? What's changing? Yeah, so the solution. So that's the tricky part, if you didn't catch that. And then it is water, and then it did tell us to assume the density of water was 1, which I was going to say if they didn't tell us to assume that. So then we know we have 100 grams of water. And so we're basically there. So now we can calculate, right, our Q. And so then that's going to be, so 4.18, again, joules, and then times our mass, so times 100. So, right, that temperatures, or sorry, grams will cancel, and then times 7.2, so Celsius cancels. And again, remember, we're in joules. So 4.18 times 100 times 7.2. All right, so then we should, and now I'm going to convert. So that's 3 kilojoules, right? But then, so now let's find how much it is for a molar amount. So per, right, because this is per 0.158 grams of magnesium metal. And so this is similar to the calculation that you did in lab, right? So now we're basically saying, okay, well, we quantified this, right? We found that this scale of reaction releases 3 kilojoules of heat. And so then what would be the molar enthalpy? So for 1 mole of magnesium. So how would you calculate that? Excellent. So find our molar amount. So 0.158, and you said 24 point, remind me, 305 grams. So excellent. So that gives us moles, which again, I believe the lab walks you through this process, but good to kind of piece it together again. All right, so then we only had 0.0065 moles. And so now we can take our amount and divide it by such. And so, right, we should get 461 kilojoules then per mole of magnesium. So excellent. And then I don't have, we could look for practice problems. Because obviously you can also take this and find like specific heats of the metals, right? So you could be given kind of 2 scenarios. And the main thing is always this heat, right? So heat is our constant between the 2 systems. And then the rest is just different variables. Let's take a look at your homework. So I don't know if there's any questions that have been difficult. Yeah, I mean that's what I was pulling up, but I'm also not opposed to looking at anything else if there are questions. Like another. Do you remember which one? Looking at the 10 grams of water. All right, so yeah, let's look at that one. So let me copy the problem over. Okay. Okay, sorry, paste it as a picture. All right, so we have 10 grams of water at 90 degrees Celsius is added to 100 grams of water at 10 degrees Celsius. And so what is the final temperature of the mixture? And so of course assume that all of the heat loss by the hot water is gained by the cold water and vice versa. So kind of think about it for a second and we'll go over it. All right, so kind of walk me through this. So what do we know? What's missing? And they give us a hint here, right? And so that's kind of what I was saying is these problems are, they all kind of are structured pretty similarly. And so let's just look at, right, kind of our scenarios. So we have our hot water. And again, we have our specific heat. So Q is equal to our mass times specific heat times our change in temperature. And so that's kind of part of the problem. And we haven't seen a problem like this yet, but we'll just back out our variables, right? So we're missing the final temperature. So we don't have the change in temperature for each one, but that's fine. We can find it. But we do know, right, Q has to be the same. And so they do tell us that. So whatever Q, right, the hot water loss is equal to the amount gain by the cold water. So you can at least start to set that up. And I'll even, right, plug in some variables just so we're not confused. And so this is going to be T final minus 90 degrees. Again, we don't know what our change in temperature is. It's going to be equal to, so then it'll be negative times 100 grams. And then, again, we don't have a T final, but we do have an initial. And then I left off the specific heat, right, since we're working with water. If this was not water, then you could just plug in the specific heat, right, for that element. Luckily, it's just the same, so that variable cancels out. Otherwise, right, just multiply it in, it's fine. So I would expect to see a different substance on the exam, is kind of what I'm hinting at. All right, at this point, it should just be algebra now, so then we just have to distribute. So I'm just going to change our variable to x so that we can have some algebra fun. And then does the setup make sense to everybody? Because it's really just the setup. And then, yeah, and then at this point, so now just distribute and double check my algebra as well. So plus 110x is equal to and so then we should get x is 17.3 degrees Celsius from that then. So it works out pretty nicely. So again, on an exam, what I would care the most about is this setup here. And then obviously, right, if you mess up the algebra, that's okay. Get some partial points. Excellent. Other questions? Let's see. I'm kind of shocked I didn't ask it as a question on the homework. So the one thing that we didn't talk about that could be on the exam is just kind of writing or sketching a diagram. So sketching a reaction diagram. And so some things that you might see, so if I were to give this to you, so let's just say we have an activation energy of 50 kilojoules, endothermic reaction, and change in enthalpy of 20 kilojoules. And so the idea is, right, can you kind of sketch this out? And so you can make some sort of diagram here. So you have energy on the y, and then this is just usually like some sort of time scale reaction. And then, again, kind of key points for an exam. So this is endothermic. So that means our products, right, will be higher than our reactants. And then you'd want to label it. So this difference in height, right, that's your change in enthalpy. So that's your 20 kilojoules. And then, right, activation energy just refers to the energy needed to go to our transition state here. So this is kind of our high energy state. And so whatever that is, and again, landing in our final product. So that's endothermic. And then I'll just kind of sketch out an exothermic one. And again, we'll use same values. So activation energy of 50. But this time, the change in enthalpy will be 20, but that's going to be negative 20. And again, just kind of do some relative sketch. So we have our activation energy of 50 kilojoules. Again, our change in enthalpy is from our reactants and products there. And so then you'd label that as negative 20 kilojoules. Energy on the y-axis, time on the x. Yeah, and then the rest, I'm just kind of looking, should be fairly straightforward. Maybe we should look at, I'm just looking at 8 really quickly on your homework. I'll write it. So it says calculate the energy change when 24 joules of work are done by the system and 15.0 joules flows in. So just pay attention to questions like that. That's a good one. And so again, right, work done by the system. So that's not favorable. So that's going to be, right, energy kind of release. And then flowing in, right, positive values. So just paying attention to those. So then obviously adding negative 24 plus positive 15 gives you about 9 joules. Negative 9, sorry. But yeah, just understanding those terms of if the system is doing work, right, then it's negative, or the system is being worked on, then it's positive. So keeping those terms straight. All right, any other kind of questions? Hopefully you feel a little better about this chapter. All right, so I do want to do a fun demo. I'll probably have to stop the stream, unfortunately. So I don't know that I'll be able to record it. But, oh, actually, let's do an intro to it. So I am going to do the thermite demo for y'all. Hopefully I don't regret it. I was debating about it for a long time just because of safety concerns. And so I think it's good to talk about, just so you know, like my thought process. So obviously I'm a highly trained chemist. I worked with pyrophorics as my PhD. Somehow I've never done the thermite demo in my life, though. I mean, it just never cropped up. I mean, it's not, unless you're welding. So that's kind of what I wanted to talk about, is this is kind of a cool reaction, and I'll show like some video. So that's the other thing I was like debating around, like, obviously there's a tons of videos, but that's not the fun part. The fun part is actually kind of doing it. And so I just wanted to talk about slightly the history of it, which is kind of cool. It was this old German chemical company, basically. Maybe I should share this video. But they were basically trying to figure out how to purify metals, which obviously, right, is important in industry. How do you take essentially, right, this mess? And they kind of talk about that in this video of like, right, you have this alloy of metals and how do you separate it? And obviously, you know, back in the day they were using, this video is kind of cool. It talks about this, like all the nasty acids and all sorts of chemicals that they're trying to use to, again, purify metals. And so that's kind of how the thermite reaction was developed by this chemical company and Hans Goldschmidt. I probably may have mispronounced that. And what's kind of cool is he did get a patent, which I just wanted to pull up. I have it somewhere. Where'd my window go? Oh, now I've lost it. But he basically got a patent back in like the 1800s. Here it is. Oh, I didn't find the patent. Here it is. Oh, I think this is a copy of it. So yeah, so this is 1897, and I think this, yeah, so U.S. Patent Office, so method of producing metals and alloys. And then I think he got a second patent later because this was used, right, to make railroad ties. So that's how they used to do welding back in the day, right? So they'd go out, you literally melt iron with this reaction, and then you can weld the railroad. Fun fact, so back in the day, MIT people pranked and like thermited a railroad car to the rails. Unfortunately for y'all, that's now probably a felony. It is a felony. I just don't know if it's a federal offense. Probably a federal offense at this rate. Yeah, unfortunately for y'all, more and more regulations come down the pipe, but that's another rant for another day. Anyway, so we're going to try the thermite reaction. Oh, this is kind of cool though, what I wanted to show. And so, again, like part of my reservations is I don't know what's a good scale. I'm running it on a pretty conservative scale, and we'll all see together how it goes. Like I said, I don't have personal experience with it. I've literally only seen it performed in person once, because most people don't like doing it. People are kind of gun shy about it. And so why that is and why I had such reservations about doing it, and I was debating it literally up until like the hour right before class, is okay, right? This reaction, well, let's kind of watch the video so we know what we're in for.
Oh boy. Oh no. Oh no. That's the end of the GoPro.
Oh, there it is. Good job.
The reaction starts at the igniter and expands outwards in all directions.
To me, it almost looks like ants or mold or something. It looks organic in how it's sort of spreading. You see a pulse.
Yeah.
Boom, boom, boom.
It's living.
Yeah, that's what it looks like.
Yeah, so like I said, I should share this video, but it's really cool what they did because they had this GoPro that they sacrificed in the process. And so they're just kind of showing the slow-mo of it. But then, right, again, let's think about the safety considerations because that's what I'm kind of thinking of when I'm trying to figure out, like, where should I perform this demo for y'all. Is so, like, literally, right, it starts becoming a molten boiling pot of liquid. Like, that is, and that's the beauty of this reaction. That's why I wanted to do it. Like, that is how exothermic this reaction is it is melting iron and then appropriate for welding. And so again, right, I have to think about it could potentially bubble over.
Why is there
safety
pulsing?
considerations,
I don't know.
Usually you kind of
Okay.
want like 4 meters space. Although I don't know that they were 4 meters back in theirs, and they were definitely using a pretty large scale. But again, so that's kind of what I'm thinking of. So this reaction has the potential, right, to kind of boil over. So that's why we can't do it in the fume hood, actually. So like if you do it in the fume hood, there's a high likelihood that we would scorch, right, all the sides of the fume hood. So we're going to try to not do that. And so instead, we'll probably take it outside. So we'll have to like parade around. And so yeah, we'll take it outside. But then I was like super, super nervous about doing it outside because the thing that could go wrong, again, right, that's the job of a chemist is to like plan like what could go wrong. And so obviously the worst case scenario would be like if there's a strong wind, right, then it could kind of maybe pick up, because what you mix in there, so thermite, sorry, I got so excited with the, because right, you have to talk about the practical considerations, but I got so excited I almost forgot to go over the reaction here. So we're going to be mixing iron 3 oxide plus aluminum. So it is literally just a redox reaction, right? So they're going to be swapping partners. And so we'll make aluminum oxide. And then, like I mentioned, molten iron metal. And if all goes well, I should be able to pull it out the iron with some tongs. And so that should be cool. But yeah, so simply, right, a redox reaction. It just is, again, extremely exothermic once you get it going. And so they will be added as 2 reagents. So that's also, again, other safety considerations that I kind of went through. So we're doing it. I believe we picked 9 grams of iron oxide and 3 grams of aluminum. So like I said, little smaller scale. If you look online, some demos say go bigger, but again, I want to go conservative because it is my first time doing it in person. And so then the other thing, other safety considerations. So these are both flammable powders. Again, I've never seen this happen. So aluminum powder is supposed to be pretty flammable. It usually doesn't just go up. And then once you mix the two together, right, that is called thermite or thermite powder. I'm not sure if that's commercially available, but this is pretty dangerous at this point, right? So now it's thermite mixture, and any spark could set it off. And so as a safety concern, so I'm going to mix them together, and I am going to kind of stir them a little bit, but you would not want to use metal, so no metal. So I'm going to grab a glass stirring rod for that. And so, like I said, I'm just kind of walking you through how this demo's been set up. And then, so other safety considerations, so I'll go through the setup of this. So we have a ring stand that I prepared, and then there's 2 flower pots. And so the reaction goes in here, so we're going to have the thermite powder. And then you need an igniter. And the typical igniter is just a magnesium strip, so that's why that's why I wanted this little guy, because I'm not sure that a regular lighter will light it off. That will be nice for magnesium. So we'll light off the magnesium, right? Obviously that'll be bright, but that is not what we're looking for. But then the magnesium should kick off the thermite reaction and then get things going. And like I said, we'll see what happens. And so this flower pot, I have a little piece of paper here to prevent, obviously, the powder from going out before we're ready. Once it starts burning, then obviously everything will be burning. There's 2 flower pots because there's a high likelihood that the inner one will crack, and I want to keep the molten thing there so that ideally the iron will melt, and then you'll kind of see it flow down. And then I have a large bucket of, we're using kitty litter, but sand would also be appropriate, so some sort of just solid absorbent material. And again, another safety tip, you would never want to use water. Some people think that water would be cool, but that would be too explosive, right? You would have hot iron molten metal going in, and then all that energy is obviously going to go into the water, which is going to make it turn into a gas and then cause more explosions, which is the effect that people are going for, but then, again, safety hazards. So yeah, all that considerations. All right, sound like a good plan? So I'm going to stop the stream. If anybody wants to record it for me, that's fine. But I probably won't be able to do that